All right, good afternoon, everyone. Can people at the back hear me? Okay. So last time we start to talk about Bayesian decision rules. What we are going to do today is to continue that discussion. I want to show you the derivations of the two other cases that we haven't been able to go through last time. And then I want to spend some time talking about this topic. It's called the minimum probability of error decision rule. It is the alternative way of getting the exact same result. Okay? So remember, last time when we defined the Bayesian decision rules, we start with all these models. We start with the Gaussian model, and then we find out the geometry, and then we draw that decision boundary. Okay? And then we say that the decision boundary is found by maximizing the posterior probability. What you are going to see in this lecture is that I'm not going to look at the posterior probability. I just want to look at the probability of error. I'm going to define it. What do I mean by probability of error? And you can see that the minimum probability of error decision rule is exactly the same as the decision rule we defined the last time. Then I will also talk about methods to evaluate a decision rule. That's called the receiver operating curve. Okay, so let me remind you where we are. So we are in the topic of linear discriminant analysis. By its name, we are going to look at linear classifiers. We are on the left-hand side of this diagram. It's called the generative method. It's a method where you want to construct a model. In our case, it's a Gaussian model. And from the Gaussian model, you are going to define the decision boundary in terms of this W transpose X plus W0. Now, the alternative approach of linear discriminant analysis is called a discriminative approach, where you look at the data sets and then just directly draw the decision boundary. That would involve logistic regression, SVM, deep neural networks, etc. Okay? So we are on here, and we want to understand the principles, the geometry, and also the performance of this method. Okay, so this is the outline. There are two parts of today's lecture. The first part is the continuation of last lecture, where we want to talk about two of the three cases. These two cases are when your covariance matrix, they are the same. However, they do have a covariance matrix. It's no longer an identity matrix. The third case is that when you have general covariance matrices. So in that case, we are going to show that the decision boundary will become a quadratic equation rather than a linear equation. Now, the second half of this lecture, we will spend time talking about the probability of error and then Bayesian decision rule as the result of minimum probability of error. And of course, the ROC curve. To start with, let me remind you what we have done last time. So last time we defined this notion called the discriminant function. And for the case of a Gaussian distribution, the discriminant function will be written in this form. The discriminant function by itself, it will be written as the log likelihood plus the log of the prior, because this discriminant function is defined according to the posterior. We are interested in looking at the posterior because typically you are given some observation. You want to claim whether this data point comes from class I or class J. And so at the back of the problem, you're solving optimization by finding the class that can maximizes the posterior probability. And so the discriminant function will just be the log of the posterior. And since Bayes' theorem says that the posterior can be written as the likelihood times the prior divided by the total probability, and then the total probability has nothing to do with your I. You can drop that term. That's how we can come up with this discriminant function. For the case of Gaussian, you plug in the likelihood function, which in this case, it would be the quadratic equation involving mu I and sigma I. So these are the class parameters, class mean and class covariance. This term comes from the normalization constant. That is the log of the determinant of the covariance matrix. And here is the prior distribution, pi I. Okay, so that is a discriminant function. And then the decision rule is, of course, you check the overall discriminant function, which is gx equals to gix minus gjx. And if gx is bigger than 0, then you claim it will be class I. Otherwise, you will claim it is class J. Again, we're doing two classes, so I and J, they're only two, they're literally just two classes. If you have multiple classes, you need to extend this idea to consider multiple boundaries. There are different rules of doing multi-classes. So within the context of two classes, then what you need to do is to check against this number bigger than 0 or less than 0. Now, you look at this equation and realize that everything is determined by mu I and sigma I. And so we are going to look at the three cases where sigma I, the covariance matrix, is the identity matrix, or the two classes, they share the same covariance matrix, or the two classes, they have different covariance matrices. So last lecture, we proved that the first case where the covariance matrix is identity. Then you can show that the decision boundary, this Gx, can be written as this equation is a linear equation. And the reason why we can get that is that you have this Gix minus Gjx. You look at the equation previously. You plug in the Gi into this equation, put the Gj into this equation. Because you have the same sigma, and the two sigmas, they are identical to an identity matrix, you can do a lot of cancellations. That's why you will you start with a quadratic equation. This is a quadratic equation. You can simplify it to a linear equation. Okay, this happens when your sigma I is identity. Now, so at the bottom of this slide, I mentioned a couple of things. If you tell me that there are two Gaussians, and you also tell me the model parameters, then I will return you the separating hyperplane. This is how the Bayesian decision rule runs. Okay? This is the best possible hyperplane according to the posterior distribution. The geometry of the case 1 is that you draw two circles. They are circles because you have the identity matrix as the covariance matrix. So we have two circles here. The centers are denoted by the mu i's and mu j's. And we know that there is a line passing from mu I to mu j. That would be the normal vector of your separating hyperplane. So you know that the separating hyperplane has to be somewhere here, and then it has to point from mu I to mu j. Now, the offset of the separating hyperplane is, of course, in the middle. And then it depends on this term. And this is the location of your y-intercept. And you see that if you don't have any term at the, let's say you don't have any pi I and pi j, you remove this term, then it's just at the middle of the two classes. But because you have mu I and mu j, they're different values, that would add to your shift. Okay? If your mu I is big, then you would lean towards mu I. If pi j is big, you will lean towards the other class. So that's the geometry of case 1. Now, we are going to look at case 2. So in case 2, we are going to assume that the covariance matrices, they are no longer identity. However, they are still the same. So when this happens, you can rewrite the discriminant function as follows. So instead of you writing a sigma I, you just replace the sigma I by the sigmas. And in class I and class J, they have the same sigmas. So you look at this equation, and then we ask, can we do some simplification to this equation? And if you look at the steps that I'm having here, the first thing I do is to remove this log of the determinant of the covariance. Why can I do that? Because at the back of this optimization, I'm trying to optimize with respect to I. And since the sigma I doesn't depend on I can just drop it, right? Okay, so now once you drop that, then you don't have the determinant to worry about. And if you look at this term, you can see that this is a quadratic equation in x and in mu. You expand it out, you get x transpose sigma inverse x plus the cross terms, and you also have the mu I sigma inverse and mu I. So you have 3 terms. Now, you're applying the same trick as before. Since this first term, x transpose sigma x, doesn't contain any I, because at the back of my optimization, I want to find the I. So it has nothing to do with I, so it will not influence your optimization result. You can simply drop that. And so when you drop this term, you realize that this GI, the discriminant function, can be written as follows. It will be mu I transpose sigma inverse, which essentially is just a vector. Okay? You have a vector transpose a matrix that's another vector. I just call it Wi. And then you have the offset. The offset is given by this quantity. This quantity contains nothing about x. So it's a constant with respect to x. So at this point, you realize that my discriminant function is a linear function in x. Now, it is different from before. And the difference is that previously, you still have the you have the identity matrix for the sigma. So if you plug that in, you realize that this, if you set your sigma equals to identity, this will be gone, this will be gone, right? So it's a little bit general than before, but it's not too different from before. Now, when you try to construct the overall discriminant function, it will be the difference between GI and GJ. So when you take the difference, you have this Wi and Wj, and then Wi0, Wj0. These are the two scalars. You put them together, then you can see that the discriminant function g will just become sigma inverse of this mu I minus mu j, this entire vector. You take a transpose, so you can define this W. And then here will be your offset. Okay, so it is still a linear classifier. So now you can also write this equation of W transpose x plus W0 in terms of this W transpose x minus x0. So now x0 becomes your offset. So once you do that, you can see that the offset, this vector will be given by this quantity minus something. Okay. Again, for sanity check, you can put this sigma equals to identity, and you will obtain the exact same result as before. So what is the geometry of this case 2? The geometry of the case 2 can be visualized in this diagram. Previously, you have mu I and mu j. Okay, so these are the two centers. You also have mu I and mu j. However, because you have the covariance matrix, the covariance matrix is no longer a identity matrix, so you will get an ellipse. You get an ellipse rather than a circle. And then you have orientation because your ellipse is not diagonal. Okay? Because if you have a diagonal a covariance matrix, then it will be either vertical or horizontal ellipse. But in general, you can have any entry in your covariance matrix that will give you the orientation. So this is the covariance matrix. And now you realize that what is the W? The W is, of course, pointing from mu I to mu j, pointing from mu I to mu j. However, there is a transformation. The transformation is given by sigma inverse. The transformation would kind of rotate your vector. Okay? So if you connect from mu I to mu j, this is the direction. Right? Now, but clearly, if you just draw the orthogonal vector to this, that would be your separating hyperplane. However, that's not the separating hyperplane because we know that these two ellipses they're rotated, and we know that this black line is the correct separating hyperplane. Now there's an angle here. This angle is really measured by this transformation sigma inverse. You do the sigma inverse because you want to rotate this dotted line to this solid line. Okay? The geometry is not too different. It's just that you can imagine that you have this ellipse, but since you rotated the ellipse, this separating hyperplane has to follow your orientation. It's the exact same root orientation. You move to the left or to the right by 50 degrees, then your separating hyperplane has to also move to the left or to the right by 50 degrees. That is the geometry. Now, the offset x0, you can see that it also contains two terms. Previously, we have this equation with this sigma equals to identity, but now you have a sigma here. But if you look at the first term, it's still the midpoint between the two centers. Okay, so that's the midpoint, and then you have an offset. This offset is controlled by this quantity. It's a little bit complicated, But never mind, it says that this would be a constant, and then there is a moving direction. There's a still mu I minus mu j, so you move from here to there. Now, when do you need to take into account of this offset? It will be when pi I is not the same as pi j. When pi I is the same as pi j, you get a log of 1, that's 0, so you can just drop the term. But when they are not the same, then you need to take into account of this term. This says that, of course, okay, but looking at this equation, you realize that I'm not going to move this x0 along this direction. I'm going to move x0 along the direction suggested by mu I minus mu j. So x0 is not moving here. Okay, you won't move off this axis. You're still moving along this line from mu I to mu j. Okay, so you're just moving this line to the left or to the right. Do you guys see that? All right. Okay, so that is the geometry of the case 2. It's still pretty manageable. All right, but then it has a little bit more expressiveness than case 1. Case 1 is just very, very restrictive. Now let's work on case 3. Case 3 says that I have sigma 1 and sigma 2, they are both different. In this case, then the bad news is that you cannot drop the sigma I. They have to be there. Then there is limited things that you can do. The only thing you can do is to rearrange the terms in such a way that I can write down a simpler equation. So what I'm doing here is that I'm grabbing all the terms in this discriminant function. I'm just grabbing the x together. So that's the quadratic form of the x. This is a linear form of the x, and this term contains no x. Right? So I have quadratic, linear, and constant. That's for gi. Now, of course, I need to calculate the difference between gi and gj. That will give you the g. Okay? If I take the difference, since all these gi's can be written as quadratic, linear, constant, I can just take the difference between the quadratic, linear, and constant. Do you guys follow me? Okay. So once you do that, then you realize what is the decision boundary? Well, you can just compute this against 0 and check whether this is bigger than 0 or it is less than 0. Now, when you look at this equation, by checking bigger than 0 or less than 0, this is just no longer linear. And so what is the separated hyperplane? You may not get a plane. Okay, the decision boundary, it could be given by a curve. So the geometry will be a lot more complicated. It's not too much complicated, but it's complicated. Okay, so now what would be the shape of your decision boundary? It really boils down to the curvature of this matrix. So you have Wi minus Wj, that is a matrix. Okay. Now, ignoring the other terms, that will be the leading term. This, if you have a positive semi-definite matrix, then you have an ellipse. If you don't, then you have some weird shape. What are the shapes? It would be like this. Okay. So there are many, many different cases. Where do I get this picture from? I got it from Wikipedia. Okay. So now, okay. So let's see. This is the easier case. This is a sphere. It happens when the W matrix is a diagonal matrix, and they're all the same. All these numbers, they're the same. You get a sphere. When does it happen? Well, this happens when, for some magical reasons, when you take the difference, they become something like this. Now, it could be that one is a bigger circle, the other one is a smaller circle. So you get another circle here. Okay, so that will be the geometry of the W. If you have a case like this, you have two positive numbers and then 1, 0, then one dimension is gone. So your decision boundary will be this. So you ask, where is the class 1, where is the class 2? Class 1 is inside, class 2 is outside. You can have this situation, you have two dimensions got to 0, then the decision boundary will look like this. Okay? So it will be 1 on this side, 2 on the other side. Now, of course, life are not easy, right? So you can have situations like this, like that, this, that, or that. Okay, you can have just many, many different combinations of the geometry. The good news is that when you solve a problem like this, you actually don't care how the geometry really looks like because you will never plot the diagram. What you will do on computer is that you give me a data point, x. X is your testing data point. You give me x. I just put it into my equation. This is my discriminant function. I check whether this is bigger than 0 or less than 0. Right? So you give me an image. I dump it into this classifier. I check whether the discriminant function will be positive or negative. Positive, I declare is class 1. Negative, I declare is class 0. I don't need to look at the geometry. Although it's very beautiful, it's very informative, but it doesn't help you in terms of computing. All right, so this slide summarizes what we do on a computer. So the quadratic classifier is not a big deal, okay, on computer. The hypothesis, what you do is really to check whether this G is bigger than 0, less than 0, or equal to 0. So when you're given a project, okay, homework number 3, you will have the opportunity to practice this. So I will ask you to construct a Gaussian distribution from the data set, and then I will ask you to tell whether a certain data point belongs to class 1 or class 2. And the two Gaussians, they will not be the same, both in terms of the mean vector and also the covariance matrix. But don't worry, all you need to do is to construct this discriminant function and calculate this score for the testing data point. Bigger than 0, class 1, less than 0, class 2. Question? Sure. Okay, so the question is the meaning of these small w's. Okay, so the w's refers to here. There's a linear term. I call this as my w. This is my small w, and then these will be a w0. Okay, so you have 3 terms. Now the geometry, of course, it depends on all the 3 terms. So all the 3 terms. Okay, so first of all, the curvature is defined by the Hessian, which is the W matrix. But then the linear term will move you to the left, to the right. Okay, so there's a linear term there. That will correspond to the case where W is equal to 0, W is not equal to 0. That just is the nature of the problem. Okay, so so it's just like the classical quadratic equations, right? You have ax squared plus bx plus c. Okay, so that might be a little bit easier to analyze. You ask what is the meaning of b? B is just the movement along the line. Okay, it doesn't change your curvature. Okay, so A will change your curvature, B will change your position, C will change your upper or lower. Okay, so that's the meaning of all these quantities. So it's the same thing in the high dimension, but just harder to visualize. Okay, more questions? Okay. Now, let's move on to talk about another very interesting aspect of the problem. It's called the probability of error. What I want to show you is the following. I want to show you that the Bayesian decision rule we have derived for both case 1, case 2, and case 3, okay, they correspond to a problem of minimizing the probability of error. If you get the Bayesian decision rule, you will also minimize the probability of error. And before I do that, of course, I need to define what is probability of error. So let's look at a 1D case. It's a lot easier to understand. Suppose you have 2 Gaussians, and then you have made the Bayesian decision based on these 2 Gaussians. So what you would do is that you look at these 2 bell curves, and then you are going to draw a decision boundary. Okay, let's say this is your cutoff. On the left-hand side of this cutoff, you will declare class 1. On the other side, class 2. And you realize that since they are overlapping, there will be error, because if my sample is sitting here, then it has certain probability that it comes from the red curve. It has also certain probability that it comes from the blue curve. Okay? although I'm declaring that this point, according to my rule, I will claim that it belongs to the blue, but it can happen that it actually comes from the red. Okay, so there is always an intrinsic amount of error. So the underlying areas, the pink areas, and also the blue areas, they are defining their probability of error. Before we move on to characterize these two errors, I want to make a comment here that this Gaussian thing, they are just models, all right? So if the underlying distribution is also a Gaussian, then your model fits the data, and so your decision will be good, okay? And so and if that happens, you will always have some overlapping between the two, no matter how far they are. The Gaussians, by definition, they have infinite support. They will still overlap, although the probability is very small, so they overlap. So no matter how you do, there will be classification error if the underlying distribution is indeed a Gaussian. But since Gaussian is a model that you choose, it could happen like this, that the underlying true distribution is a square box. Who knows, okay? If that happens, then your Gaussian will not make any error. Because the Gaussian that you're using is the model that you put onto the data. And you never know whether the model you put onto the data is actually the data that the model generates the data. Okay? So there are two different things. One is the model that generates the data. The other one is the model that you use to make your decision. They're two different things. Okay? So the model can come from Poisson Gaussian or something. And then you say that I don't care, I'm just going to use Gaussian. Then with model mismatch, you can still do something, right? And you can still get a decision boundary. It will still work. But then when you ask how well you will perform, then you need to check against the underlying generative model who generates the data for you. So this picture is showing you this mismatch here. It could be a good mismatch. It could be a bad mismatch, right? So this is showing a good mismatch where the underlying distribution, there are two boxes. All the samples, they're drawn from these two boxes, okay? And then you say, you go to the data set, you say, I don't care about what you have, and then I'm going to put two Gaussians on top of you, and then I'm going to estimate the model parameters. And I will get two Gaussians, and then I will find a decision boundary, okay? And then the decision boundary will be here, and then I test on this true data set. It'll be perfectly fine, okay? Although there are model mismatch, you're perfectly fine because your intrinsic data set, there's no harm that you make a decision here or there, all right? So you see, there will be mismatch between your model and also your choice of model and the underlying model, okay? And then when there's a mismatch, it may not always be a bad thing. Usually it's a bad thing, but it's not always a bad thing. So when we want to quantify, then there is error in your decision boundary. The typical assumption is that the model that you use to make the inference matches with the model that generates the data, okay? So the underlying model is Gaussian, and you are so fortunate that you are also using the correct Gaussian, okay? If that happens, then we can clearly quantify the probability of error. If there's a mismatch, there's one more layer of complexity that you need to resolve the model mismatch issue. So in this half of the lecture, we're going to make an extremely restrictive assumption that the data itself is coming from a Gaussian, and the model that I use to make the inference is also Gaussian. Is that point clear? All right. Okay. Now, if you agree with my problem setting, then we can define the probability of error as follows. What is the probability of error? You want to calculate the error where it should be class 1. However, you declare that it is class 2 or class 0. Okay, so what is it? Well, let's say you have, this is your observation X, this is your label Y. Okay, when X is less than tau, you are going to claim that this is class 0. However, your class label is 1. So that is clearly an error. Okay, this is an error because these two things cannot happen at the same time. Or the other case where you declare that X belongs to class 1 because it's bigger than the threshold. At the same time, you know that the label says it is 0. So that would define the error. Okay? So it would be the intersection of your decision versus the ground truth. Okay? And then you need to sum these two errors. One corresponds to here, one corresponds to there. So we have two pieces of the error. Statisticians like to call them type 1 and type 2 errors, which I never remember how to differentiate them, so I'm not going to go into the details, all right? Okay, so but then we can calculate these two quantities. How do we do that? Not that hard, okay? So look at this. This is the intersection of two events, and by very simple definition of the conditional probability, you can write down the conditional probability that x is less than tau, given that y is actually class 1 times the prior probability that class is 1. Okay? This is undergraduate probability, right? So it is n can be translated to conditional times prior. Same for this case. Now, when you look at this quantity here, there are two terms. Okay? The first term is a conditional probability that given class is 1, what is the probability that your observation will be less than tau? And since you know that you're working on Gaussian, you can just plug this number into your Gaussian PDF, okay, where you're evaluating this Gaussian, given that you are looking at class 1, now you have two Gaussians, each Gaussian you have a mean, you have a variance. So now you have a class 1, you're just looking at what is the probability that my x is less than tau using mu1 and sigma 1, okay? Now, what is this prior probability? That's just pi 1. You do the same thing for the case of class 0. So you have pi 0 times Gaussian PDF evaluated at x bigger than tau in class is C0. And to calculate this Gaussian distribution, what you are literally doing is integrating the Gaussian PDF from -infinity up to the point that you care, which is tau here. So you put in your Gaussian PDF with mu1 and sigma 1 for the first case. You integrate from minus tau to tau. And then for the second case, you're integrating from tau to infinity because you're looking at x bigger than 0. And in here, of course, you're putting mu0 and sigma 0. Okay? This is a very complicated quantity, but it defines the probability of error. It is the probability of error, okay? So the following thing could be a little bit magical. We ask, how can we minimize this probability of error? Okay? So what we do is that, can we try to take the derivative of this gigantic thing, setting it to 0, and let's see if we can obtain a solution. If you take the derivative of this probability of error with respect to your tau, now what is tau? Let me remind you. The tau is the decision boundary. It is the cutoff that you want to find out. Okay? Now, of course, here there are two parts of the story. Here I'm saying that if I tell you the tau, what is the error? Part 2 of the story is that suppose I want to find the best tau, what is that? Okay? This part shows you, you tell me the tau, that would be the error. This is doing part 2. I don't know which tau to use, but I want to find the tau that can minimize the error. So if you follow the derivation here, you can see that I'm taking the derivative of the probability of error with respect to tau. And so I need to take the derivative of this integral. But that's not the end of the world, because we know that taking the derivative of the integral can be done using a thing called the fundamental theorem of calculus. It says that when you take the derivative of this integration, this tau can just plug into whatever you have inside the integral. Okay? So that's freshman calculus. So you do that, and then you realize that, okay, this is a Gaussian equation. You put the tau inside, you just replace any x by the tau. So you end up having this equation. It's just the PDF of Gaussian evaluated at tau. And here it will be a Gaussian distribution evaluated at tau with a minus sign coming out. Okay? So you have these two quantities ready, then the calculation would become pretty straightforward then, because plug these two numbers in, setting it to 0, then what do we have? You have an equation of pi 1 times the first Gaussian, and then pi 0 times the second Gaussian. And then I want to make my life easy, so I just set sigma 1 equals to sigma 0 equals to sigma, case 1. Okay, actually case 2, okay, case 2. Because this is a 1D version of the case 2. You set that equals to a sigma together. If you do that, then you can see that in this equation, setting to 0, you can just cancel out these two terms. And then you move the things around by putting the log on the two sides, and then do some magic, buy a coffee again, do a little bit algebra, and trust that my calculation is correct, then you get to this point. Okay? You compare this result versus the result that I showed you before. They are identical. Okay, this is just the 1D version of whatever I've shown you in case 1 and case 2. Okay, so this is the cutoff, and so any x, so as long as my x is bigger than tau, you will declare that the point belongs to class 1. Less than tau, it belongs to class 0. And this is the decision boundary. The decision boundary, 1, it is the Bayesian decision rule according to the derivation that we have done last time. 2, it is also the same decision boundary coming from minimizing the probability of error. And therefore, my Bayesian decision rule is indeed the rule that minimizes the probability of error. And that is the best I can ever achieve if your underlying distribution matches with my model. Okay, you cannot do better than that because I am already minimizing the probability of error. How can I do better than that? Is it okay? So that is really the optimal, that's the optimal. No matter how many deep neural network you use, that is the optimum solution. Okay? All right? So if you bring me a 30-layer deep neural network, it's not going to be better than this because the underlying distribution is indeed Gaussian, and then I am using a Gaussian. So and then I'm minimizing the error, so I am the best. Is that point clear? All right. Okay, so the optimality of the Bayesian decision rule is that this is your rule, and then you are making the decision between 1, 0, and otherwise, and then these are the conditions that you have to check. And this is the exact result as the Bayesian decision rule I just described. Okay. However, optimum doesn't mean that it's error-free. Okay, I want to make this point very clear. Optimum just means that the error is minimized. It doesn't mean that you can make perfect decision. If your underlying distribution is overlapping, it's unavoidable to have overlaps. Okay, if the overlapping is unavoidable to have errors. It's just the part of the problem nature. Okay. Also, I want to make it very clear that minimizing the probability of error does not imply that it is the best. Okay. Now, you need to define what is optimal. You need to define what is the best. It could be that by minimizing the probability of error, you could miss some cases. Now, let me show you why. Okay, the thing can happen when you are solving a problem like disease. Okay, so you have two classes. Okay, whether the patient has this cancer or not versus the other they don't have cancer. Okay, so two classes. And then when you try to do experiments, you know that the probability of getting a cancer is actually very low. That's just it's just the nature of the problem. Okay, so if you follow the probability of error rule, you know that one part of the error is unlikely to happen. It's just, okay, but then 99% of people, they will be normal. And so a good decision rule, according to minimizing the probability of error, is just to declare everyone is healthy. If you do that, the probability of making an error is low because the number of patients who actually get cancer is few. Okay, that rule, you declare everyone is happy, that is healthy. Happy means healthy, right? Okay, so if you declare that, then the probability of error is minimized. That's a terrible classifier because if you miss a cancer case, the person is going to sue you because this is United States. Okay, so you realize that there's a big problem here. The cost of making a wrong decision of that case could be a lot more significant than the normal cases. And so by minimizing the probability of error does not imply that you have a good decision rule. There are more other things to worry about, okay? And that's why there's another set of whole literature on things like a minimax decision rule, which says that I want to make sure that even the worst case is well controlled. It makes lots of sense. I want to make sure that if a person gets the cancer, that part is well taken care of. Or putting it on the other side, I want to make sure that the healthy persons, their detection rate is about a certain percentage. But I want to maximize the performance of the cases that I care about, right? So just be careful when I say that the Bayesian decision is optimum. It just means that it's optimum with respect to the probability of error. If you agree that the probability of error is good, that is good, okay? But if in your problem setting the probability of error itself is not the way to define optimality, then having a Bayesian decision rule is just not solving your problem. Okay, so there are two levels of optimality, okay, which I want to make it very clear. The one part of the optimality comes from a finite training sample that is within the problem scope. That says that I only have 20 samples for class 1, 50 samples for class 2, and therefore my estimate of my mean vector covariance matrix, they are not that accurate. Okay, so that's one level of error. That can be compensated by grabbing more data points. The other problem is due to the intrinsic problem of your problem, which is the geometry of the problem, where you really have overlapping between the two classes. Okay? So there are two levels of optimality. I will also add that there's a third level of optimality. It really depends on the problem, the problem type, the application that you're working on, which would define what we really mean by optimum. Okay? All right, so to summarize the discussion about the medical example, here is what we really care about. We are not just caring the probability of error, we care about something called the risk. The risk is defined as the probability of error, however, they are weighted, okay? This is 1, 0, okay? So it depends on, okay? So there are two weights. This way, we put certain emphasis on the cases where you have a miss, okay? So he has a cancer, but then you declare that he doesn't have a cancer. That is a missing case. The other one is a false alarm case, okay? I'm using the more engineering terminology, okay? Statistics, they have type 1 and type 2, which I never remember which one versus which. Okay? So now you have these two cases. Okay? So you have these two cases. So false alarm, you may want to put less emphasis on false alarm because we are okay with false alarm. Just like our fire drills. Okay? Just let it sound. I just close my ear. Okay? But then miss, you need to pay a lot of attention to, because if you miss one, you're going to penalize a lot. So you can put different weight on these two. Okay? That would define the risk, and that risk is actually the thing that you care about. Okay? Every problem should have its own risk. If you're working on the airplane problems, the aircraft, and then you want to make sure certain locating the direction of the aircraft, the miss will be very important, because if you miss that, that would be a catastrophic problem, okay? Sometimes when missing a student, copying another student, it's okay, okay? Because it's not that big deal, okay? So think about what kind of risk that you really cared about when you look at your problem. Okay, so by false alarm and detection, I can also look at these two terms more carefully. I can define the miss as this yellow area, and then the false alarm as this blue area. The complement to this blue area is called the probability of detection. Okay? And then you can define a curve. It's called the receiver operating curve, ROC curve. Perhaps you have heard this term before. The ROC curve is a curve that shows the probability of detection versus the probability of false alarm. It is this pink area over the blue area. Okay. So once you have this information, then you can plot a curve, and any point on this curve will be corresponding to a particular decision rule. Okay. It's a function of tau. Tau is the cutoff threshold that you choose. Okay, the optimum one. Okay, the optimum one is given by the Bayesian decision rule, which minimizes the probability of error. Is 1 point on this curve. All right. Now, whether this point is good or not, that's debatable. Okay. So you change to another tau, which now you move away from the Bayesian decision rule. Basically, it could be that the Bayesian decision rule says you want to have a tau equals to 0.5, and now you choose 0.2. It's still a decision rule. You can still compare your data point with that threshold. It will still give you a decision. Where does it go? Well, it would just be another point on this curve. Okay? So when we say that we want to minimize the probability of error, it will be 1 point. If you want to minimize the risk, it would be another point. Which point is good? You tell me, okay? You are the user of this problem. And then you tell me, what do you care? And then I will look at the curve, I will say, okay, since you want to have false alarm rate no bigger than certain level, and so that will be the operating point. Okay, because say this false alarm rate, I don't want it to be more than, I want to cap it less than this. Okay, so this is a maximum false alarm rate I can tolerate. Okay, don't give me more false alarms. Then what would be the best operating point? Well, it would be this point. Because why? Because you want to maximize your detection. You always want to maximize your detection. Okay. Now you ask, okay, now I want to maximize my I want my detection to be at least 75%. So how much false alarm that I need to handle? It will be at this point. Okay, so you tell me how much you can afford. I tell you what will be the point of operation. Okay. So here is the ROC curve, and interpreting the ROC curve is that normally what you do is that you compare two different classifiers. If one classifier, my 30-layer ResNet, is performing better than your VGG16, I should expect to have a curve that is uniformly higher than your curve. Okay? Don't just report me 1 point. If you only report me 1 point, then it could be that you're operating at this point and then I'm operating at that point. And then that's like an apple to orange comparison. Who knows which one is better? Okay? So normally you need to report the entire curve to tell people, to convince people that over no matter which decision you have, I am going to be better. So that's the ROC curve. And there are lots of things about ROC curve which we don't have time to go into details. However, I would encourage you to take a look at a few lectures, okay, materials. One is this chapter, Do the Hard and Stock, on pattern classification. They have a lot of discussions on this ROC curve, probability of error. I want you to take a look. Another place where you can get a lot of help from is ECE595, where we have a lot of discussions on the meaning of this ROC curves, the convexity of this ROC curves. Why do you see some examples where the ROC curve is not concave, but there is staircase behavior, so there will be a lot of discussions over there. Okay, I will also type like an appendix later on tonight to tell you the difference between ROC curve and also the precision recall curve. They are pretty much complementary to each other. They all derive from the same diagram. All right. Okay. So let's resume our discussion on Monday.